So I'm going to be talking about critical points. So there's two main types of critical points, local extrema and absolute extrema. The difference between the two is, if you'll notice, here and here are 2 points. So those are where the graph roughly changes direction and starts moving. It reverses direction on the y-axis. So those are local extrema. Now, absolute extrema would be the absolute greatest point on the graph, or the absolute minimum point on the graph. So if you'll notice here, these are arrows instead of endpoints. Now that means that this graph will continue on into negative infinity and positive infinity. Some graphs don't have local extrema, so their only extrema are negative and positive infinity. So here I'll show you how to calculate for maximums and minimums. So this equation, it's a polynomial, and it is on a local interval, so -1 to 3, not negative infinity to positive infinity. This has a set endpoint. So you take the derivative of this, which you'll get 6x minus 10, and you want to take that derivative and set it equal to 0. That'll help you solve for your extrema. So once you set equal to 0, you get x equals 5/3. Now what you want to do, because you only got 1, you want to take that number and make sure it's between -1 and 3. Okay, it is. And you want to plug all 3 points into the original equation. So I've just done it really quickly, and I got f of -1 is 20, f of 5/3 is -4/3, and f of 3 is 4. Now, from this local interval, you find your absolute largest number and your smallest number. So your largest number is your maximum, and your smallest number is your minimum. So because this interval happens to overlap the absolute minimum of the original function, then this is your overall absolute minimum. Okay, so here we have Rolle's theorem and mean value theorem. So these two are quite similar, but they have some key differences. So there are some conditions that need to be met to satisfy each one of these theorems. Rolle's theorem needs to be continuous and differentiable, and that's the same with mean value theorem. It also needs to be continuous and differentiable on the interval that you are solving for. So what that means is, with Rolle's theorem, is you have to have your interval be equivalent to each other. So they have to have the same y-coordinate. So by having the same y-coordinate, what you're doing is finding at which point there is a tangential line that it has a slope of 0. So in other words, you have a derivative to find the slope of c, which is your original function, and you set that equal to 0 and solve. It's pretty easy, it's pretty straightforward. But with mean value theorem, you get a problem of inequality between your starting and end point for your interval. Now that means that it's not equivalent, and the tangential line you find in the middle of it will have a less likely chance of having a slope of 0. So basically, there's a little formula for this. You take your endpoint, you plug it into the original function, and you subtract your starting point, which you've also plugged into the original function. And then you divide that all by the end minus initial, or final minus initial, and basically you solve, and you set that all equal to the derivative of c, or the original function. Now, that will find your slope between the two intervals, and these are just two different ways to do it. One is if you have equivalent starting and end points, the other is if you don't. So that's that.
So the first derivative test is used for when a derivative of a function changes signs on a graph, and the first derivative test is used to find the local extremum at that point. So in this example, you have it going in a positive direction, it's stopping, and going in a negative direction. That is your critical point right there. And what these critical points and local extrema are depends on if the function is moving from a positive and then switching to a negative direction like it is in this one, or if it is moving from a negative direction to a positive direction like in this one. You have, in this example, the critical point would be at the function's maximum, and in this example, the critical point would be at the function's minimum. And now for the actual test in what you have to do mathematically to figure out these extremum. First, you have to find the critical points. This is done by setting the function equal to 0 and then solving for that. And then you have to draw a number line with the critical points on it. Then test numbers on the interval in the first derivative. So take the first derivative of the function and then test the numbers on the number line in that function. And then finally, state whether the function is increasing or decreasing. And now I will show you an example. All right, so here's our example for the 3.3. Again, the first step is to find the critical points. By doing that, you need to find the derivative. The derivative of this equation is 4x cubed minus 12x squared. Now you must set this equal to 0. And for simplicity's sake, you can take out 4x squared from this equation. So and so now you have a more simplified equation. You can easily get the critical points from this by setting each of these parts of the equation equal to 0. And the critical points are 0 and 3. And now we put those in the second step on a number line. So over here, 0 and 3. And now you basically test points within these two intervals as to determine, in this function up here, as to determine whether it's moving positive or negative at these in-between points. So for 0, you can test -1. You plug -1 into the equation, and it turns out to be it's negative. Take 1 and plug it in the center here, where you have it here, and plug that into this equation, and again, you get a negative number. Plug something like a 4, which is about 3, into the equation, and you'll get a positive number. So there are our movements and for the graph. Now, the last step is to determine where it is increasing and decreasing. That's easy. It's increasing, of course, from 3 onwards, so increasing 3 to infinity. It's decreasing because it's decreasing from 2 points here. It's negative infinity to 3. And now that we have this, we can determine that the minimum, because this is changing from a positive to a negative direction, the minimum is 3. So minimum 3, which is your relative extrema. So 3.4 has to deal with a second derivative test. And this second derivative test can be used only in certain situations for functions. If the function has a CP where the derivative of x equals 0, and for these certain situations, if the function is positive at this point, then the function has a local minimum at that point here. But if, however, if the function has a CP where the derivative of x equals 0, and the second derivative is negative, the function has a local maximum there. Now to get to the actual test of what you have to do for this, first find the second derivative of x equals 0 and find where it does not exist. It's pretty simple. Basically do what you did for the first derivative test and then do another derivative of that. Then plot those points on a number line, that you get those critical points on a number line again, but instead of where in the first derivative test you plug them back into the original function, you plug them into what you got for the second derivative. This will give you your several points, and then you need to test, it'll show you which is not only your points but the concavity of your function, depending on, I should draw that here. So a concave up would be this, and a concave down would be this. And so this will show you what your function would actually look like on a graph. And this is honestly only important for what you get for the point of inflection, which is where concavity changes. And this is determined by an example that I will show you. So here's our example for 3.4, the second derivative test. You have here your function. Now you take the first derivative of that function, which is 12 minus 3x squared. Now you set that equal to 0, and you get 12 3x squared. And for this, your x's would be positive and negative 2. And now you plot those points on a number line over here, negative 2, positive 2. And again, like you did for the first derivative test, you plug in points in between those, either to the left, negative 2, or to the right, negative 2, and then to the right, positive 2. And you get it being negative over here, positive right here, and negative right here. Now you can determine where it's increasing, decreasing, and the max and minimums are. So here are increasing negative 2 to positive 2, decreasing negative infinity to negative 2, and also from 2 to positive infinity. And now the minimum is, as you can determine, is at negative 2, and the maximum is at 2. And now you have that, you can take the second derivative of this, which would be negative 6x. Because you can't really do anything with this, the only thing that you can get here if you set it equal to 0 is x equaling 0. You do a second number line and plug in points again to that formula, and you get positive and negative on positive to the left and negative to the right. And now you can determine where it would be, where the concavity would be up and where it would change. This is where it changes, and so concave up would be at negative infinity to 0. Concave down would be from 0 to positive infinity, and the point of inflection is obviously at 0.